Bismillahirrahmanirrahim. Greetings. The topic of this video lecture and a few more to follow is about mathematical concept of relation and function. Now, I intend to give my lectures to the level of college algebra and pre-calculus, and also the students in majoring in liberal arts, freshmen in particular, they will hopefully benefit from these videos. Now, since functional relation is involved with a set of order pairs, in fact heavily involved with the order pairs, set of order pairs, I feel like to designate this video to talk about the concept of set and a little bit about history of that. And so set, like a point, like a line, plane, and a space, is in the list of undefined terms. Now, this is to prevent circular definition. Now, for instance, in a junior high textbook, you may find that the line segment is defined to be a segment of line that includes both of its end points. You notice that in this definition is using the word line to define line. Now then, how are we going to define point and line and plane, let's say? Now, I have seen some textbooks, they define the point to be intersection of two lines. By intersection, I don't mean superimposed of each other. So intersection of two lines. Then we ask, what is line? Then we go and try to find out what is the definition of line. We notice that they are defining that to be a set of points. So point is used to define line, line is used to define point. You see, you are going around circle. So then the question comes, what do we do with these undefined terms? They are keystone. They are keystone for all other definitions to be built up. So we have to start from a point that we can no further define that term. And these terms, like set is one of them, in fact, set and point and line and space and plane, they are undefined terms. Now, how do we deal with them? We deal with them kind of intuitively. We get a mental picture out of them. And for instance, point we consider as having no dimension. Line to be one dimension, which means has length but has no width or thickness. And the plane has length and width but does not have thickness. And now then the question that you may ask is that I have seen almost all textbooks, they define set to be a well-defined collection of objects. I repeat myself, well-defined collection of objects. So they say that is definition of set. So if set is not defined, how come they are making that definition? Now, looking at it analytically, think and reflect, critical thinking, you notice that this definition is circular. Now, how is it circular? He says, listen again, I repeat myself. Set is defined to be a well-defined collection of objects. I will be coming to this well-defined word or word which is play very important in this definition, so-called. Now, here the collection of objects is synonym, is equivalent in meaning as the word set. So in other words, he's using the word set to define set. But in order to make it to sound better than literature, he is not using the same word set, but synonym of that, which is collection of objects. So you can see the circular definition in there. Now, this definition also leads to a contradiction and paradox. One of them is known as the Russell paradox, that I'm going to go over that, and I will put it on the board, bulletin board. I hang it that and go over that one. Now, this founder of set is a German mathematician by the name Cantor, and he kind of classified the infinite sets. And there is no rigorous mathematical proof or analytical proof for his claim, but there is a very good persuasive illustration that at the time that he published his idea, it was ridiculed and rejected, and he was humiliated in a sense by contemporary mathematicians of his time. But now, the great mathematician that we have, his illustration, his demonstration is acceptable. Now, I'm not going to go through that because internet, you can Google it and find out so many of them. But if I may notice any comment from you in the comment section that you are interested to see my way of presenting that, the one-to-one correspondence between, say, a set of counting number and rational numbers, then I will be happy to do that. But internet and YouTube has quite many of them. And also there are a few other paradoxes like Barber paradox and Gilbert Grand Motel or Grand Hotel. I will go over them before the end of my lecture. Okay then, now let me zoom this one if I may. I go over the one-to-one correspondence between counting number and set of rational numbers. But before I go to that, let me say a few words about what I just said a few minutes ago about well-defined. What is that crucial part of well-defined in that definition? Now, a set of short people. Now, grammatically, the sentence could be complete. But logically, we notice there is a hole in there. And the hole is in there is what? The set is not well defined. The well defined part is missing. Do you follow me? Now, I am 5 feet 8 inches tall. And among the midgets, I am a tall person. But among the NBA, the national basketball players, I am a short person. So a set of short people is not, the well-defined part of it is missing. In other words, a set should be what? We should know precisely what is in there and what is not in there. And the definition that we accept as a definition, well-defined collection of objects, even though it is circular in reality, it is acceptable because he gives us very good intuitive picture, intuitive meaning of what set stands for. I repeat myself, we know exactly what elements is inside the collection and what elements may not be in there. So it's well defined. And that is sufficient because it gives us a good comprehension and understanding of what set stands for. Now, I'm not going to go for the union and intersection and complement and how to combine sets, etc. But I'm going to go through the Cantor one-to-one correspondence and talk about that short. Kind of not too deep, but more the detail and you can find them in internet. It's much more detailed than I can talk about. So let me zoom this one for you, if I may, and go over that for you. Thank you. Now, we are all familiar with the set of counting number, positive integers, 1, 2, 3, 4, 5, and so on and so forth. Now, this set of positive integer and the set of non-positive integer, which means negative integer including 0, these two sets, we notice that the set of integers looks like it's twice as large as set of what? Set of a positive integer. You see that is twice, because it doesn't have negative, but this does have the negative of exactly same counting number. So it's a common sense to accept this one being twice bigger than this. But it is strange and absurd to say that these two sets, they have same number of elements. There is one-to-one correspondence between counting number and the set of entire integers. Again, it sounds absurd, but I'll go over that. Now, I give you another one which is sounds more, in a sense, absurd and strange in a sense, and that is between the set of positive integers, counting number, and the set of rational numbers, there is one-to-one correspondence. Now, the set of rational numbers already includes the set of counting number. So how in the world can we have one-to-one correspondence? Now look, set of rational number, 0, 1, 2, 3, 4, and so on and so forth, -1, -2. Then between 0 and 1, just that single interval, there are infinitely many rational numbers. That I have put some of them for you. In other words, they say, in fact, between any two rational numbers, there is another rational number, which is the average of them. So the set of rational numbers is a dense set. So between 0 and 1 alone, there are infinitely many rational numbers, as I have put some of them for you to see. Now, the same goes between 1 and 2. There are infinitely rational numbers between 1 and 2, not including 1 and 2, that they are not counting number. They are not positive integers. Between -1 and 0, also there is infinitely many rational numbers that they are not what? They are not positive integers. They are not counting number. So how in the world can we put one-to-one correspondence between them? And what does one-to-one correspondence mean? It means that there are same number of rational numbers as there is counting number. Again, it sounds absurd, doesn't it? But there is no analytical proof for that. There is no rigorous mathematical proof for it. But there is a demonstration. There is an illustration that is very persuasive and acceptable, that in the time that Cantor presented that, it was rejected. It was not accepted and it was ridiculed. But all of our mathematicians today, they accepted. How to demonstrate this one, to put one-to-one correspondence, again, you can find it in the internet, and I intend to put possibly one video lecture, which is not going to be too long, just about showing the one-to-one correspondence. In other words, there are same number of rational numbers as there is counting number. Again, seems absurd, but it's reality. Now, just to go over that, as a matter of fact, the set of rational numbers, is countable, yes, but we cannot put order to them. We cannot say, for example, 1, 2, 3, 2 is larger than 2, 2 is larger than 1, as located to the right of 1. We cannot do that to the rational numbers, because there are so many of them. So if you notice the definition of rational number in the textbook, they say the set of all a over b, where a and b are integers and b is not 0. I don't have to say b is not 0, I didn't put it here, because if b is 0, we are not dealing with numbers to begin with. So there is no need really to mention it. So this is the way that set of rational numbers presented. Now, also, I will go before the end to relate that one to relativity, to the Einstein relativity, and see some kind of correlation maybe is between them. Now, with your permission, let me go to another one, which is about the Russell paradox. I said I will go over that for you. And let me maybe zoom this one also better so that I can discuss this one a little bit better in detail. Now, what Russell is a British philosopher that he came with this paradox. Now he said that the well-defined collection of objects, even though the well-defined is there, still will lead to this paradox. Now, let's say I have a collection of all those sets that they do not contain themselves. No, there are infinitely many finite sets. Like the set of 1, 2, 3 does not include the same set 1, 2, 3. There is only 1, 2, 3 in there. So if you want to include the set of 1, 2, 3 also, so you say 1, 2, 3, then you open a bracket, you write 1, 2, 3 in there, in that bracket, close it, then close the bracket again. If you do that, then that finite set has 4 elements. One of them is 1, second one 2, third one is 3, and fourth one is the same set, 1, 2, 3. So the set 1, 2, 3 become an object in that set. Now, Russell says, let S to be the set of all those sets that they do not contain themselves. All right? So he collected all of them. There are infinitely many finite. He put it there. Let's say integer, the set of integer doesn't include itself. 1, 2, 3 doesn't include another set in there that is 1, 2, 3, 4, and so on. Bracket, bracket. So same is true with set of rational numbers, set of real number, and any set we can think of. All of them that they do not include itself, he puts it there, the collection of them. Then the question he asks, he says, what happens to the set S? That is the collection of all those sets that they do not contain themselves. So if it doesn't contain itself, then must be there. Because it's all the elements in this set, in this S, are those that they do not contain themselves. So if it doesn't contain itself, must be in this set. And if it is in this set, then it contains itself. Do you see the contradiction, the paradox? So it's only one drop in the ocean in reality. It's not a big deal to make Cantor very upset of that, and people start to ridicule him or so on. Unfortunately, in the history it does happen. Okay, now also let me say, I have put it in writing, yes, fortunately, and I also may want to zoom this one, about the Barber paradox, and also we'll go over the other one that I mentioned about Einstein's relativity. Let me zoom this one also. It looks like it's a zoom good enough. Okay, I have already gone to Russell paradox. I have written, if you are interested, to write it for yourself. Now the Barber paradox is that there is a barber in a town that he claimed that he shaved all those that they do not shave themselves. So those that they do not shave themselves, he shaved them. Then the question is, does he himself shave himself? If he shaves himself, he doesn't shave himself. If he doesn't shave himself, he shaves himself. So you can see the contradiction and paradox. Do you see that? So another one we have is called Gilbert Grand Motel. That is very, very interesting. He shows what the infinite said, and about contemplating, in fact. And that one, I was going to, in fact, to put it, to make a video out of that, but I noticed that YouTube has many of them, quite few of them, and they have done it animation with the Gilbert Grand Motel. So the other one is infinite, they call it also infinite motel paradox. So please look at the YouTube, because I don't have that skill to do animation, to do as good job as they have already done. So I do encourage you to watch that videos. There are quite few of them, but few of them are very, very interesting and very explicit to get the feeling how the set of infinity works. Okay, now if I may, let me zoom it. Now, in closing, I would like to say something about the theory of relativity. He says that, Einstein's theory of relativity, he says that if an object is moving very fast, let's say less than the speed of light, but fast enough, then an object that is moving with the speed of light, he comes and passes from that object, the object is going with the speed of light, and 1 second later, it will be 3 times 10 to the 8 meter ahead of it. It looks absurd, huh? Because the object is already in the state of, the first object is already in the state of motion and is going terribly fast. So 1 second later, you should not be expecting that the object that is going with the speed of light to be 3 times 10 to the 8 meter per second ahead of it, which is the speed of light. But that is the theory. Now, this theory, of course, has no, again, rigorous mathematical proof or any analytical proof. It's a theory. But as far as the Gilbert the Grand Motel is concerned, very interesting. I encourage you to watch it. And also the one-to-one correspondence between counting number and rational number, there is illustration. There is that is acceptable, it's very persuasive, as I already mentioned. All mathematicians of our time, they accept it. So there is no rigorous proof, there is no analytical proof, but the demonstration is persuasive enough. But as far as the theory of relativity is concerned, there is no way you can really to provide any kind of evidence or proof, illustration or mathematical proof for that. Okay then, I thank you for watching, and I try to prepare some good other videos for this, for coming, and I wish you all prosperity, and please stay safe. Thank you for watching, and have a great day.